All right, so what we're going to do here is carry on with chapter 5. The other day we started to look at the multiplication rule, but before we did that, we introduced a few new ideas here. Specifically, we were looking at what we call joint probabilities. Let's go back a little ways. A joint probability is the probability of two events both being true at the same time. For example, what's the probability that a randomly chosen student from this student body is getting a bachelor's degree in finance? Now, of course, that means two different things are true. That means that they're getting a bachelor's degree, which comes from this first row, and they're studying finance, which comes from this first column. At the intersection, we find there are 130 students who are getting a bachelor's degree in finance. And when you divide that by the grand total of 500, you come up with a probability of 0.26 or 26%. So this is referred to as a joint probability because two different things are true at the same time. Okay, now what about the other probabilities? How about marginal or unconditional probabilities? Well, what are we doing here? We're simply looking at totals. In other words, the unconditional probability that a randomly chosen student is getting a bachelor's degree is 400 out of 500, because altogether we have 400 students working on their bachelor's degree for every major, that is. And then altogether there's 500 students in this student body. So this probability is 400 over 500, which is also 0.8 or 80%. And then the most interesting one, the trickiest one, would be the so-called conditional probabilities, which are the ratio, as you can see here, of a joint probability to a marginal probability. For example, what if we pick somebody from the student body who is known to be working on a bachelor's degree, and we want to know the probability that that student is majoring in marketing. So this is very different because now we're told that B, the probability B is a known event now. And now the question is, what's the probability that this bachelor's student is studying marketing? So what that means then is that we can do two things. First, the probability of getting a bachelor's degree in marketing is written as B and T. Remember, T is being used to represent marketing. From the chart, that represents 0.18. Okay, here we have the actual probabilities. In the previous charts, we had the raw numbers. So let's go back and look at that one. In other words, 90 would be out of 500 would be that probability because there's 90 students getting a bachelor's degree in marketing out of 500 total, which means 0.18. Or with this chart, you can see that that probability has already been calculated for us. We went through the entire chart and calculated these probabilities by dividing each of the totals by 500. So B and T, or the probability of getting a bachelor's degree in finance, marketing rather, is 18%. Now, we also need to know, to calculate this probability, the probability that the student is just getting their bachelor's degree, which we've seen earlier is 0.80 or 80%. So the ratio of these two is what we're actually looking for. 18% out of 80% represents 0.225 or 22.5%. So in other words, over here you can see that this is what we were told. This isn't something that we know to be true. And with this information, the question becomes, what is the probability of majoring in marketing given that they're getting a bachelor's degree? And of course, don't forget this symbol here represents given that. Okay, so in other words, given that this student is working on their bachelor's degree, what is the probability that he or she is studying marketing? And that's 0.225 or 22.5%. Now, just T by itself is not going to give us the same answer because if you look at this chart again, the total for T is right here. So while it's a small difference, they're not identical to each other. What that really indicates is that the proportion of students who are studying marketing is different between the bachelor students and the master students. That's really what this means. So this is what we mean by a conditional probability. Now, in all these cases, if you notice that what we are doing is we're taking the joint probability of these two events, T and B, and then we always divide by the marginal probability of this event. And that's how all of these conditional probabilities are calculated. All right, now with all that being said, we are now in a position to define formally the multiplication rule, which we know is used to represent the probability of a joint event. Okay, now if we don't happen to have a handy table that we can use like we did here, uh, well, then we need to use this rule. Okay, the table's nice, but we don't always have the whole table. Sometimes we only have bits and pieces of information, and so that's when we really need this rule. Now, there's two equivalent ways of doing this. Let me copy this up here so you can see them together. And you can see they are different. Here's B given A times the probability of A. Here's A given B times the probability of B. Now, if you want to memorize these and you don't want to forget, just remember these two are the same. Okay, I don't know if that helps or not, but this is one way you can help yourself memorize this rule. Okay, now, so for example, we had this case last time. The probability, first we pick a card from a deck, and A is defined as the event that the card is an ace. B is the event that the card is black. So the question is, what's the probability that the card is black and an ace? In other words, what is the probability that this is a black ace? Now, we know from our knowledge of the deck of cards, there's only two of these aces, the ace of spades and the ace of clubs are both black. That's it. That's all we have. And since the entire deck has 52 cards, this probability we know already is 52, 2 out of 52. Or if you want to reduce it, you can rewrite it as 1 over 26. Well, now what we want to do is demonstrate this in two different ways using the multiplication rule. All right, so we've got two choices. So with the first approach, let's say we choose to go this path. All right, what do we need to know? We need this information, B given A, and just A by itself. All right, now the conditional probability is always the trickiest one. How would that work? In English, this is the probability that the card is black given that it is an ace. Now, there's 4 aces in the deck. The ace of spades, clubs, hearts, and diamonds. These are black and these are red. So that means that if we know that this is an ace, the probability of it being black is 2 out of 4 or 1/2. And again, you're just literally counting the number of ways this can happen given that the card is an ace. If we didn't know that, then this answer would have been 2 out of 52. But because we know that this is an ace, that reduces the probability to, or increases it rather, to 2/4 or 1/2. So that's the hard part. The easy part is the A, the probability of an ace, just plain ace, is 4 out of 52. There's 4 aces in a deck of 52 cards. So if you multiply these together, actually you can reduce this one to 1 over 13 if you want. So therefore, what we're aiming for is this. And after I've reduced these both, 1/2 times 113 is of course 1 over 26, or 2 out of 52. And of course, it's exactly what we found earlier when we noted that there are in fact 2 black aces out of 4. In the entire deck, there's 2 black aces out of 52, which means the probability of randomly choosing a black ace is 1 out of 26. Okay, well, let's try it this way. B times by the way, the sequencing of these is irrelevant. I just want to mention that right here. Both of these mean the same thing. And in addition to that, the order in which you write out the elements here, or the events, A and B is the same as B and A, okay? All right, now, so we're gonna try this approach. So what about A given B? What is the probability that the card is an ace given that it is black? Okay, Well, you have all the black cards, 26. And here's the red cards. We can basically ignore these right now because we know that it's not a red card. Out of these black cards, 2 are aces. So that means that we have 2 out of 26, or 1/13. Then we have the probability B of being a black card. And again, half the cards are black. Half of them are red. Therefore, this probability is simply 1/2. And the product is 1 out of 26. Again, we already knew that. Okay, so this just confirms that we already knew that this probability is 1 out of 26. All right, now you'll recall that when we were looking at the addition rule, there was a special case when we were able to simplify it a little bit. That was when the two events, A and B, are mutually exclusive. Here we're introducing a different concept. It's possible for two events to be what is called independent. And basically what that means in English is that the occurrence of A does not affect the probability of B, and vice versa. So you could imagine a lot of examples of when this would be true. For example, what if we had something like this? We observe tomorrow's weather. This is our random experiment. A would be the event that it rains, and B is the event that it is between 50 and 60 degrees. Now, I'm not a meteorologist, but I'm pretty confident that these two are not going to affect each other. In other words, there's nothing to stop it from raining if it's between 50 and 60 degrees, and or whether it's not 50 and 60 degrees. So we could say here that A and B are independent because one occurring does not influence the probability of the other occurring. I mean, that's basically what we're looking for. Okay, now on the other hand, if let's try a silly example here. Let's change it to A is it rains, and B is it is between 20 and 30 degrees. How about that one? Well, A and B are not independent because one occurring rules out the other occurring. In other words, it obviously can't rain if it's between 20 and 30 degrees. So if we know that it's between 20 and 30 degrees, then A can't be true. It must be snowing instead of raining, and vice versa. Okay. So anyway, that's what independence is. But now we have a much more formal definition of it that we'd like to address right now. So here's an example of a deck of cards. We have a card chosen from a deck. And what's going to happen here is that we're going to do the following. We're going to take a look at the card. And let me just draw a little picture here so you can visualize what this looks like. Here's a deck of cards. Let's make it 3D here. I pick a card, I take a look at it, and here's the key detail. I put it back, and then I pick another card. So why is that relevant? Because what's happening is that when I pick the second card, what happened on the first card does not affect the likelihood of the second card having any particular value. So this is sometimes called sampling with replacement, because once I've drawn a sample from my, in this case, my population, which is a deck, before I draw another sample element, I'm going to put the first one back so then the entire population is still intact. Okay. Now, this diagram is very clumsy, obviously, but what it's illustrating here is that when you pick the first card, you put it back before you pick the second one. And that guarantees that what happens on these two draws are independent of each other. Now, obviously, we could have the opposite case as well. In other words, imagine that we have this case where we pick the card and then we don't put it back before we pick the second card. So this is called sampling, as you can probably guess, without replacement. And this guarantees that the two cards do depend on each other. In other words, what happens to the second card depends on what happens to the first card. Okay, in other words, if the first card is red, that reduces the likelihood that the second card is also red. All right, so that's what this is all about. So in our specific example, we are sampling with replacement, and the events that we define are the first card is red and the second card is red. Now, because we're sampling with replacement, it should be clear that the two events are independent of each other. Okay, what's the probability that both cards are red then? Well, we know already that a deck of cards has 26 cards, of which half are red and half are black. So each of these events independently of each other, the probability of A is a half, because there's only 26 red cards in the deck. Now the second draw, though, now here's the interesting part. What's the probability that the second card is also red? Given that the first is red, it's also a half, because the first card was put back. So when we pick the second card, there's still 26 reds out of 52. And so this means then that the probability of B given A is the same as just B without any knowledge of what happened to A. And so they're both 1/2. Now that's an important detail. What it means is that whatever happened to A did not affect B. And so the probability of them both being red turns out to be a half times a half, which is a quarter. So formally, two events are said to be independent if the following two conditions are both true. All right, so what's actually happening here? In the first case, A does not affect B. How do you know? Because having this information does not affect the probability. The probability of B given A is just the same as the probability of B, which means that A is not affecting B. Whereas down here, it's the other way around. B does not affect A. How can you tell? Because knowing that B is true is not affecting the probability of A. So in order for two events to be considered independent, both of these conditions must be true. Okay, one is not good enough. All right. Both must be true for independence. If one or both of them are false, then the two events are not independent. Now, why is this important? Because now we can define a simpler version of the multiplication rule. And so all of a sudden, look what happens. You lose all the conditional probabilities. In other words, this was B given A. This was A given B. Not anymore, because these are equal to each other when A and B are independent. So look how much simpler that is. The probability of B and A being true is simply equal to the probability of both of them independently being true multiplied together. Wow, that's helpful, to say the least. But I think it's intuitively clear why this must be happening, because each event is not affecting the others. Then the probability of two of them being true is just equal to the multiplication or product of each one individually. Okay, now we're getting into some deep waters. This is Bayes' theorem. What's interesting here is that Bayes, Thomas Bayes, was one of the more influential figures in statistical history. And the ironic thing is that he wasn't a mathematician, he wasn't a statistician. He was actually a Protestant minister who happened to dabble in this stuff in his free time. and he came up with these results that actually revolutionized statistics. In fact, there's an entire branch of statistics, rather, called Bayesian statistics, which takes a very different approach than the rest of traditional statistics. So this is an application of conditional probabilities. What we're going to do is assume that there's some event whose probability depends on a series of other events. And what we're effectively doing is taking our sample space and breaking it up into pieces. Let me show you how that would work. Here's our sample space. I'm using a Venn diagram for this one. Let's just say that we've got the entire sample space is broken up into 3 pieces. Now, the important thing about these A's is that the A's are mutually exclusive. And their entire probability, well, let's just put it that way, their union is the entire sample space. So these events form what we will call a partition of the sample space. Now, then there's another event, B, which overlaps with these 3. And so knowing if A1 is true or A2 is true or A3 is true, that will affect the likelihood of B being true. Okay, that's an important detail. So in other words, B itself has a specific probability that depends on which one of these happens to be true. Okay, now, with all that being said, there's a formula that we can calculate. This is a conditional probability formula, but it only applies when we have this so-called partition in place. But if we do, then we can calculate conditional probabilities using Bayes' theorem. All right, so let's take a look and see what, now it looks scarier than it is. Like so many results we've seen up to this point, it looks a lot scarier than it actually is. So don't panic when you see it. Okay. Oh my God. Now, you notice how we have a summation here, because this is meant to be a very general expression. If we have a partition like the one I just described, what happens is, let's say I pick A2 just at random. I'm going to have the following. In the numerator, I have this expression, which basically represents the probability that both B and A2 are true. In the denominator, I have the total probability of B occurring at all. In other words, B, given that A1 is true, probability B, given that A2 is true. And I see I'm running very desperately low on space. So this belongs in the bottom too. Okay, so in other words, that denominator is this, and this adds up. This is simply the probability of B. This is simply equal to the probability of B and A1, A2 in our case. So you can see there's nothing mysterious here. We already knew this. But what's different now is that we're actually obtaining these 2 probabilities with our conditional probabilities. Okay, so I know it's very complicated, but we can do it. Okay, so the denominator is just B broken up into these 3 components. And this is just the joint probability of B and A2 being true. You can see this we already knew. Once we have a partition, we can take advantage of it by expressing this as what we have here. All right, now once we see an example, you can relax and say, oh, that's not so bad. Look at this one. Suppose that the probability that the economy recovers next year is 20%, and the probability that we're in a recession is 80%. So this means we have a partition with two events. A is 20%, and A1 and A2 is 80%. Now, depending on which condition we're in, which situation we're in, there's a potential for a stock market crash, which is event B. So B is the stock market crash. And obviously that depends on whether or not we're in a recession. If we're in a recession, that probability will be higher. And in fact, they're telling us if we're in a recovery, oh yeah, the recovery is this one. This is the recession. If we're in a recovery, the probability of a stock market crash is very low, only 10%. If we're in a recession though, that jumps all the way up to 40%. Okay, now, what do we actually want to know here? Well, we're going to be presented with another conditional probability, which can be answered with all of this information using Bayes' theorem. Okay, so what could that be? If the stock market crashes, now remember that's B, what's the probability that the economy is in recession? Now, you can rewrite that as what is the probability of being in recession given that the market crashes? In other words, this is P, the probability B given A2. Now, we just got through seeing how this is done, right? Right, oh, no, no, it's the other way around, sorry. I just realized I wrote it backwards, sorry about that. This is A2 given B, and this is what we did earlier. Yes, A2 given B. It's easy to get this backwards, believe me. Now we're good. And that's what we just did here. So you can see this is the formula that we would use to calculate this probability, except that the partition only contains two events. So it's a little bit simpler than what we did earlier. Okay, so if A1 is the recovery, A2 is the recession. These represent all possible states of the economy next year, which means they're a partition. So we know the probability of A1 is 20%. Remember, that's a recovery. Okay, wow, that's a pretty gloomy prognosis here. We know these are the unconditional probabilities. And by the way, because these represent a partition, if you notice, the two have to add up to 1 because they represent the entire sample space. B is the event of a stock market crash. B complement would mean no crash. Okay. Similarly, the probability that there is a crash, given that the economy is in a recovery, is B given A1, and the probability that there's a crash, given that the economy is in recession, is B given A2. These are, of course, conditional probabilities, and we've already seen that these probabilities are 10% and 40%. Okay, I wrote that back here somewhere. Yes. Okay, so we can gather all that up and finally answer the following question. If the market is observed to crash, what's the probability that the economy is in a recession? That's this probability. That one. Remember, here we know the state of the economy, but not whether the market crashes. Here we're saying if we observe a crash, what's the probability that we're in a recession? So it's basically backwards from what we have already been told. So here's how this would be done with Bayes' theorem. So this is the formula with only two events in the partition. Okay, remember there's only two. And B is the crash. So what we want to know is this: what's the probability that we're in a recession? So we already have all these numbers. Okay. The probability of a crash during a recession, remember, was 40%, and there's an 80% chance of a recession. Now in the denominator, we need two terms: the probability of a crash given that we're in recovery times that probability of a recovery, plus what we have in the numerator, the probability of a crash given that we're in a recession times the probability of recession. So according to this, if we do observe a crash, there's a 94% chance that we're in a recession. Okay, now I know this is a very, very complicated topic and we're going to need some time to wrap our heads around it. But when we get enough practice, don't you worry, everything will be fine. We'll understand it very quickly. But you can see this would lend itself very nicely to medicine, where you can ask questions like this. If somebody, let's say, has a positive test for some disease or other, what's the probability that they actually have the disease? That's the kind of question you can answer with Bayes' theorem. And in fact, this happens all the time in that area of medicine. Okay, so for our purposes, this is enough for now. Now, what's coming up next is chapter 6. Now, chapter 6 is introduces a lot of very important new concepts, which are tied together with what we've been doing mainly in chapter 5. And also, this is the first chapter where the calculator will become enormously important, because a lot of what we're doing here is in fact built into your calculator already. So this is an exciting chapter. It's an important one. It lays a lot of foundations for what comes after. But and on top of all that, the calculator suddenly will come to your rescue, so to speak, in a lot of cases, because it can already help you do a lot of these problems where the formulas themselves are actually quite complicated. So what I'm proposing to do here is finish up this in the next part of this recording. This part is finished now. I'm going to stop it right here. And then the next part should be ready maybe tomorrow or the next day. And so then we'll have caught up with where we would have been had we had our normal class on Monday. Okay, so I want you to have this first so you can dive into this material, and then the rest should be ready no later than Monday morning when we would have had our normal class. And then of course on Tuesday, everything will be back to normal. All right, everything will be back to normal. All right, so anyway, so we'll stop this right here, and then in our next recording, we will introduce these so-called discrete distributions, and we'll start to learn more and more about our calculators. All right, so I'll see you next time.